Alright, so now we're going to do an ionic equation using an acid-base neutralization reaction. So in this case, again, anything in the aqueous form is going to fall apart in the solution, and it's going to be able to float around until the molecules react with each other, and in this case you're going to get the acid and the base to come together to form water and the salt. So we've got water as our product and salt as the product. So anything that's in the aqueous state we can write in the ionic form floating around in solution. So we'll do that for a total ionic equation. Alright, so when we do that, we have to make sure that we include the same number of atoms on both sides of the equation for our balanced reaction. So in this case, we've got two HCl molecules, so we have to represent both of them in our total ionic equation. So that coefficient gets distributed to each of the ions in the solution. So we've got 2 protons and 2 chloride ions. And then our magnesium hydroxide falls apart, and we can see that each molecule of magnesium hydroxide has 1 atom of magnesium, and it's got 2 molecules of the OH anion, or the hydroxide anion. So we have to include our 1 molecule of magnesium, Mg2+, and the 2 anions, the 2 hydroxide anions that fall apart from this molecule. So it becomes a coefficient here because they're each floating around separate from one another. So you've got plus 2OH. On this side of the equation, our water is not going to change because it's in the liquid state and these are now covalently bonded. So they have to stay together. They don't fall apart in the solution. So we've got 2 H2O molecules in the liquid state. The magnesium chloride is still in the aqueous state, so this is going to fall apart. So we've got the magnesium 2+, and then for each molecule there's 2 chloride ions that are going to come off of there. So we see that as the 2Cl-. So the next thing we need to do is to draw our net ionic equation, and we do that by canceling out the things that are the same on both sides of the equation. So we can see that on both sides of the equation that there are 2 chloride ions still, and that there's a magnesium ion on both sides. The H+ and the OH- change from one side to the next. They're present on the right side of the equation, but when they bump into each other, they form a covalent linkage and they create the water molecule in the liquid state. And so they are what's overall changing in the reaction. And so that's how we're going to end up writing our net ionic equation. So overall, in the total ionic equation, we cross off the magnesiums and we cross off the chloride ions. They stay the same on both sides of the equations. And our net ionic equation then is going to yield 2 protons plus the 2 hydroxide ions to yield 2 waters of molecule. So overall, in an acid-base neutralization reactions, this is a key component that's going on. The acid component's reacting with the base component to form the water molecule. And this is what releases so much heat when that covalent bond is actually forming. So we'll see when we do some acid-base reactions in the lab that it actually gets very warm and it'll generate a lot of heat when these reactions are going on. So overall, these are the steps that you're going to need to take when you're writing your net ionic equations. The first thing you want to do is to balance your equation. Once you have a balanced equation, you start by writing the total ionic equation. And you do this by breaking apart all of the aqueous molecules in the reaction. So anything designated with the AQ symbol, you're going to break apart into the ionic form. They're floating around in the water solution. If you have any solids, liquids, or gaseous materials in the solution, they are going to remain as they are, because these guys are covalently bonded and they cannot break down into independent ions. So next, when you're writing out and breaking apart your ions, remember your rules. Coefficients have to be distributed and subscripts have to be moved to the coefficient position. So when you're breaking apart your aqueous molecules into their ions, the coefficients need to be distributed. So in this example, if you had 6 sodium chloride molecules in the aqueous state, you could write them out in their aqueous form by writing each of the ions. So there's 6 sodium ions, 6 Na pluses, plus 6 chloride ions, 6 Cl minus. Okay, so you also place the subscripts into coefficient positions, and you multiply them with the existing coefficients when necessary. So if we have an example of magnesium chloride, there's 2 chlorine atoms per magnesium molecule. So when we write that in the ionic state, we'll split up the magnesium into 2+, and then we have 2 chloride ions that are present. If we had coefficient in front of this, so we had 3 magnesium chloride molecules, when we break this up, it's going to turn into 3 magnesium 2+ ions, and then 2 times the 3 for the chloride ions, or 6 chloride ions. Alright, so the third rule for breaking apart our ions is that the polyatomic ions stay together to form their ions. So if magnesium sulfate is an example, we would break apart the magnesium into its ion and the sulfate into its corresponding ion. If those ions have subscripts that are associated with them, they still have to be distributed as coefficients when you write them out in their ionic forms. So if we have aluminum sulfate, there's 2 aluminum ions in each molecule of aluminum sulfate, so that would be 2 Al3+, and we can see that there's 3 sulfate ions per molecule. So in the ionic state, when they're floating around by themselves, that would be 3 SO4 2- molecules. So once you've got your ions written out in the total ionic equation, you want to cancel out what's the same on both sides, and then you can rewrite it as the net ionic equation. So that's kind of a summary or a guideline for building your total and net ionic equations.